And so I'll start presentation on our work on type prototype model for visual medical image segmentation. A common strategy. Just a second. So a common strategy for visual segmentation is this prototype-based approach. In this approach, we first extract pixel-wise feature vectors with a neural network, and prototypes are obtained from support images. So in this case, we when we extract the features, we take the average to get prototypes. And in order to segment query images, so we extract features from the neural network, and given the query image features, we calculate the distance with the prototypes to decide whether this its feature if this feature belongs to class this class or this class, and by doing so we can segment query image. In medical imaging, the foreground class usually refers to the target organ of interest, while so for instance, in this image, foreground class would represent maybe this region or this region, but in binary segmentation setting, we would only have one foreground class, but in multi-class segmentation setting, we will have multiple foreground classes. And the background is just defined as the remaining areas. So it can include, other organs, or maybe, also this blank empty areas. So because of that, because of this, background class is usually very inhomogeneous. And standard prototype-based approach for visual segmentation uses directional separation in the feature space. So the challenge of this approach is that background class is highly inhomogeneous. As I explained in the previous page, so it is difficult to represent the background class with only a few prototypes. It is even more challenging in the case where we, for the visual segmentation setting, because we will only have few support images. So to overcome this, recently proposed recently proposed model called ADNet focuses on modeling the foreground prototypes. I'm not sure. ADNet focuses on modeling the foreground class. The foreground prototype is in this point, and because by doing so, it achieves what we call inside-outside or IO separation. And so, so instead of doing directional separation, but using IO separation makes it distinguishes the inside region from the outside region. So you can see that this approach will be more advantageous when we use a segmentation, because background class is hard to represent with only few prototypes. But by using IO separation, we can represent. We can focus on representing the foreground class. So the ADNet is the previous work from our group, and so it is. It is the previous model that achieved IO separation. So it works by assigning anomaly scores to each spatial location using fixed threshold at inference for segmentation. So as shown here, when we for feature vectors of query image at location R, we can calculate the cosine similarity with my foreground prototype, and by multiplying some scalar value, we can define anomaly score, and by using this, we can calculate the class probability for foreground class for pixel location R. So it is just defined by 1 minus sigmoid function, and it is using this anomaly score, and by subtracting some threshold. But there are 3 drawbacks of ADNet. So because it is, it is only using a single foreground prototype, and because of that, we cannot represent complex, diverse, diverse representation in foreground class. And another limitation is that it can only work for binary class settings. And there is also following work called ADNet plus for multi-class segmentation, but it cannot do multi-class training, because it is basically piecewise binary classification model, so it cannot improve the representation to representation from multiple classes. And in ADNet, it used the fixed threshold, so it cannot adjust for varying organ size or and the variability in the patients. And in our work, we propose type-to-type model, or TPM. It is the probabilistic reformulation of ADNet, and this model provides a general form of IO separation to address drawbacks of ADNet. And the key idea of TPM is to use a shared or tight center position for the foreground and background classes. It used the shared center location for the foreground and background class distributions. And we only defer their standard deviations. So in this one-dimensional example, both foreground and background classes share the same prototype, but we assign smaller standard deviation parameter for the foreground class. And recall that the standard prototype model assigns distinct prototype locations to the foreground and background classes. And because of this, we achieve directional separation instead of in IO separation. So given our assumption, tight prototype assumption about class distributions, we can drive the pixel level probability of foreground class using Bayesian theorem. So this is the foreground class for pixel location R, and this is the class prior for the foreground class, and this is the class prior for the background class, and this is representing the class distribution. We assume it to be Gaussian distribution, so you can see that they share the same position, prototype position, but they differ in standard deviation. So by doing so, TPM assigns higher foreground probabilities to features close to the prototype, and this property is useful for separating typical foreground features from non-typical background features. And in our paper, we also show that TPM generalized the previous iOS. It generalized the ADNet, so it enables some extensions. One extension is to use multiple foreground prototypes. So this can be achieved by using Gaussian mixture model for foreground class and using the same prototype for the background class. And so this enables capturing diversity in foreground class. And we can also see that even though we have multiple prototypes, you can achieve IO separation. So you can, even in the case where there maybe foreground class is quite large. For example, a liver class, the foreground is usually large, and it is hard to represent with only a single prototype. Even in such case, by using multiple prototyping, we can model the complexity in the foreground class. And another extension is multi-foreground class segmentation. So in its simplest form, this can be achieved by assigning distinct prototypes to each foreground class. So this enables distinguishing features from other foreground classes, while still ensuring the IO separation as visualized in this image. And this formulation also enables multi-foreground class training to achieve, to more effectively separate different foreground features while still maintaining the IO separation. And in addition to these extensions, we address class imbalance in medical image segmentation by introducing the ideal class prior, or ICP. It is a principled method for estimating class priors to improve the decision boundary. So it is, when we consider the TPM formulation, it tried to find the sort of the optimal class prior to improve the performance. So it is just done by just matching the number of predicted foreground pixels to the number of true foreground pixels. And in our experiment, we used two abdominal data sets, abdominal MRI and abdominal CT. And we compared previous, ADNet and ADNet++. And there are previous IO separation models, and we compared them with our model, TPM. And we considered two classification settings, a binary classification and multi-class segmentation. So, there are differences that for binary segmentation, we only have one foreground class, but for multi-class segmentation, we have multiple foreground classes. And maybe I'll explain more details, but in general, in the binary segmentation setting, we found that ICP and multi-prototype approaches improve dice score. And in the multi-class segmentation setting, ICP and using the multi-foreground training approaches improve performance. And this is multi-class segmentation result from with the single foreground class training. And this is the foreground. This is the ground truth result. Ground truth, and this is based on the ADNet++, the previous IO separation model. For the multi-class segmentation, and this is based on our model with estimated ICP. And we can see that using ICP tends to move the decision boundary close to the object boundary. Maybe it is not so much visible, but you can see that its decision boundary for this class is more close to the object boundary for this class. In summary, TPM is the probabilistic reformulation of previous IO separation model, and it generalized. It provides general IO separation, and it allows multi-foreground, multi-prototype extension for improving foreground diversity. And multi-foreground training for improving representation modeling. And we found that ICP can enhance segmentation performance. So, so thank you for listening. So.